Today we will see the Maxwell's equation in various forms for the time varying fields. These equations are very important in general. Everywhere these equations are used to solve the different problems. So what we have seen that Maxwell's equation for the static fields comprise of we have four equations, and for the time varying fields now these equations have changed to incorporate the time varying nature of the fields. So here we have one in the point form, here we have the integral form, and we see that these two equations remain intact, they have not changed. That is, the divergence of D is equals to the volume charge density. Similarly, divergence of B will always be zero. These two equations remain same. However, these two equations have changes to incorporate this change time varying nature of electric and magnetic fields. So now the curl of E equals to the minus del B over del D. That is the minus the rate of change of the flux at that point. So here if B is constant, it is not changing with time, and automatically it will become zero and will lead to the previous equation. Similarly, curl of H now incorporates del D over del T. So in the static fields, this is for the all only for the conduction current, that is the curl of H equals to the conduction current density. Now this new term have added, and this term del D over del T is called the uh, displacement current density. That is, this is the current which is coming out due to the rate of change of the electric flux density, or you can say the electric field. So D is related to the electric field. So if the electric fields are changing with time, then this will give rise to the displacement current, and this term is have the unit of the displacement current density. So now it has two parts, one is the conduction current density and another is the displacement current density. So now these equations are in the final form and you can apply it anywhere. Maybe they are if they are static fields, you can apply them. If they are the time varying, they can also apply these equations. Similarly, they are in the point form or the differential form. We are saying the point form because you can apply at single point, you can find a single point. However, the point form has a limitation, then it can be applied when the medium is discontinuous. That's abruptly we are from moving from one medium to another medium which has different characteristics. Then we can say these two medium have the boundary interface which is discontinuous. So we can't apply the point form at those points which are lying on that discontinuous interface. But the integral form can be applied in all cases. And this integral form we use to found the boundary conditions for different problems to find the value of electric and magnetic fields. So here what we have now the integral form. This is Gauss law, which is says that the total electric flux crossing the closed surface, if you have a closed surface, crossing the surface is equals to the total charge enclosed by that closed surface, that is the volume, total volume it have. So whatever the total charge is enclosed, it is equals to the total flux crossing this one. This is derived from the Gauss law. Similarly, you have for the magnetic fields, you have a total magnetic flux crossing the closed surface is always be zero. Why it is zero? Because the it is also be same as the total magnetic charges, but magnetic charge uh, comes into pair, they all remain in pair, we can say they are in the pair. So if you have a negative magnetic charge, you can say there is always be a positive charge. We can't have a mono charges, so that's why they will become zero. So total magnetic flux crossing the closed surface equals to zero. Then third term now becomes that the circulation of uh, E equals to the minus del over del T of this total flux, and this is the voltage induced, and this is called the Faraday law. Similarly, circulation of uh, magnetic field is equals to the total current passing through that surface enclosed by this contour. And this current comprises of two parts. One is called the current due to J dot ds, this one and this one. And second part is the displacement current, which comes out due to these two dot products. So we have total current now. Again, the current remains same, that it is equal to total current. Now for the time varying field, the current comprises two parts. One is the conduction current, another is the this displacement current. Okay, so these are the Maxwell's equations, which are very important, and you have to remember these equations. And everywhere now onward they will be used, and also in the higher courses, these equations will be frequently used to solve the problems. So these are the points which I have summarized here. You can go through them. And then now next topic is the time varying potentials.